Okay, everybody. So we reconvene for the last talk, which is on feed-forward 3D reconstruction. And to unpack what that, all right, I'll talk into the mic also, so I have, yeah, both for you guys and for the recording. Well, so to unpack what that is in this context, this course, we have the first word is feed-forward. Does anyone know what that could refer to? Does anyone have a theory? Yes, neural networks is correct. So there's an recurrent and feed for neural networks. So this is talking about that we are doing deep learning here. And the second part is more self-explanatory. This is 3D reconstruction, the thing we have been learning in this course all along. So this topic, let's see here if we get, yes. This topic is very closely related to the exact work you have been doing in this course. I think one goal with this course is to learn how to do a full structure for motion pipeline. So taking raw input images, just RGB, and produce point maps, relative poses, some things like that. The goal of feed-forward reconstruction is to use a neural network to do this instead. So kind of it's a rival to your knowledge here, but hopefully complementary. Uh, well, so I'm not sure if you are familiar with the Colmap, but the final project in this course will kind of be a Colmap, which is kind of the golden, like really the gold standard for 3D reconstruction. It has been for almost a decade, I think. Or something like that. And so Colmac, for example, you run sequentially two image pairs, exactly like you have done, compute matches, relative poses, then you chain these together in some type of fashion, and then you get global point maps and align them together, and then do a bundle adjustment. This. Yeah. So basically exactly what you've done in this course. And I think, I'm not sure if you've seen this kind of stuff, but I think it looks pretty cool if you collect images taken from tourists. I assume this is in Rome. You can get these very cool things. So you can just basically get all these point maps, and all these red things are cameras. So this is what you could potentially do with the knowledge you have in this course. The problem with this is I'm not entirely sure how long it takes, but I would imagine at least a day or two to run this. Because you need to run very large bundle adjustments, you need to do large chaining all these image pairs together is quite a tedious thing to do. So there's also global other methods. But so we will instead look at doing this with neural networks. So one approach one could take is just take parts of the call map. Oh, by the way, also interrupt me for questions. Please do this if you have any. So everyone is caught up. So you could just replace the parts of this. When I say call map, I also refer to what you have done in this course, like the final project. You could just replace parts of the final project with neural networks. So this is kind of like stitching it together. You could do key point detection. So you have kind of, I don't think even you've thought about this too much because OpenCV does this for you, but you have to decide on which points do I want to possibly match. And then you do the matching, right? But the points you possibly want to match is usually like edges or things that are easily recognizable from two images to another. So you could just replace this with a neural network. I'm doing some self-promotion because this is always what people do with this talk. So we have done that, at least partially, with some collaboration. And you could also just take the matching part of it where you try to compute. So in your project, you have, or the assignments, you have used SIFT to describe your key points, and then you have computed kind of some KNN matcher or something between SIFT points. You could also just replace this with a neural network, and that's we also have done. But so this you could do, and you could also do this for relative pose or bundle adjustment. This has also been done, but feed-forward reconstruction, at least how it's framed today, is kind of replacing all of it with one neural network. So rather than just stitching things together and doing bundle adjustment on top, you hopefully could get the full pipeline. I think we'll skip over these, and if we have time, I can go into how we did this matching and key point detection and stuff like that. But I don't think it's so important for the main topic of this talk, which is doing the whole thing with a neural network. Uh, so yes, I took this slide from the original VGGT, which is very popular, and he kind of jokingly said that then yeah, you don't really need to learn this multiple view geometry, so you don't need to be Andrew Sisterman. And here, yeah, you don't need to be Frederick Hall, or you don't need to know this course at all. That's at least what some people would claim, but the counterpoint to this will also come. But it's like that's hard to build. You cannot build this. The guy who built this pipeline, he definitely took this type of course before. So at least you need to do it if you want to build these networks. But so the main topic here is kind of what you see in this picture, which is a little bit, but you just take in pictures, RGB, then you have a neural network, and then you get a 3D scene reconstruction. So that's the gist of it. But then, of course, the devil is in the details. But I think, yes, for context also, what Joseph and Etienne talked about is kind of can be used on top of these reconstructions. So once you have like a point cloud and relative process, then you can do all these fancy novel view synthesis, like Gaussian splatting, all these things. I mean, you can do these things some of these things without having process, but this is one way to do it. But this is directly kind of in what our domain for this course. Okay, so this is a very, very hot research topic. So it's, if you are interested in research, I think it's pretty cool computer vision part, because these things have become very, very popular. And partially I assume it's because look cool, and also because robotics people seem to like this, but that's it, I guess. The work was really, I mean, some people did it before, but I'll start here with DUSt3R, which is pretty cool name, I think. Well, also, raise of hands, how many people have taken the deep machine learning course at Chalmers? Okay, so roughly half. Okay, so that's great. Well, so these are neural networks, right? So somewhat of black boxes, but we take the DUSt3R works on image pairs. So it's kind of what you guys also have been doing, working on image pairs, but analyzing them with neural network. So in this case, it maybe I'll go into some of the details because I think since half of you have taken deep machine learning, it might be of some interest. But what you first do is you have this image, which is possibly 256 by 256 or larger, but let's take this for an example. Then you patchify it, meaning you take small instances of the image that are locally like square, that are non-overlapping, and you have these together. These are represented by these squares here. So these could be, for example, 16 by 16. Then you'll have also, which is nice math, but then you'll have 256 of those small tokens. And the same will be done for the other image. You will thus get a encoding of the image information. So you will go from 256 by 256 to a smaller kind of coarse representation of the image for both of the images. Then you will have another transformer which you feed this representation in. So transformer, they work on tokens, and I will not bore you with, because not everyone has taken all this deep machine learning, but I think it might be of interest still. So because transformers are quite in fashion, so it might be of some interest. Well, transformers, they work on sets, so they have kind of no ordering. They just process pairwise similarities between tokens. And here we have tokens from both images. And what you do then is you have a transformer decoder, which takes the tokens from one of the images and the tokens from the other image and do cross attention between them. So this is exactly analogous to how in the original transformer paper you have tokens coming from, let's say, if you want to translate English to French, you have tokens from English cross-attending to tokens in French when you do the decoding. So this is kind of analogous to this thing. And then in the then you have some type of head. You could have a linear head and more fancy things, and output points. So now you output points from the two images. So it's kind of like depth maps or 3D points that you can see in the image one, and points you can see in image two. So these are these red and blue things. But here is the kicker, I suppose, from this course, what you need to know, or you don't need to know, but what could be useful when you try to code this yourself is what is the so we're predicting point maps. Point maps are 3D, where you have three coordinates and then X, Y, Z, and then you have some number of them. But what is kind of the challenge here in what point maps should we predict? Do you have any ideas for any challenges that might come from predicting point maps, or what do we even mean by point map? In what reference frame are we talking about here? So how would you go about solving this problem? Does anyone have any suggestion on how to predict the point maps? Like in what reference frame should they be represented? Well, one way to do it, I suppose, if you insist on not giving any suggestion, you could just choose one of the cameras and say this is the identity reference frame, and then you predict the point maps within that reference frame. Then you get kind of an asymmetric architecture, and this is what they have done in DUSt3R. So yeah, you can basically see by the blue and the red dots here, they kind of predict the depths, I suppose, but it's also could call them point maps because they're aligned in the first reference frame. So they're global coordinates, but in the reference frame of the first image. So yeah, then you have your 3D points. Uh, Well, yes. So there's a bunch of data sets where people have collected a bunch of points, a bunch of images. For example, this Rome scene we saw before. You could scrape Wikipedia or something like that for all of these images, and then you could run your project there and get a bunch of depth maps, poses, and everything. So you have basically everything from there. Then you can supervise this by transforming the ground truth points. I will not go into. I mean, we can revisit this, but I sense that we might be going too much into details. But you could just take those predicted points from here and transform the global ground truth 3D points into the same reference frame of the first image. Then you have kind of apples to apples comparison between the point maps, and then you can just do a L2 norm, like just how close are you to these points, and learn through that. And that's basically what they do, but then they add a confidence score here. Which looks more fancy than it is, but I suppose the confidence weighted loss here in the end just means that the network is free to choose how to penalize its loss itself, but it also is penalized by choosing too low confidence for everything. But so, for example, in the sky, it might be very hard to estimate accurate 3D points because they are like points in infinity, right? And also they scale. That's another problem that I could ask you about, but we will not go into there. But you could imagine that it's problematic having different scales of different scenes. So the network, is it a metric scale? Is it what scale is this depths or point maps in? So they just rescale everything by kind of dividing by the third coordinate, so you get everything in like some type of or yeah, they normalize the point maps. Well. This is yeah, the data sets of the yeah, I don't know. That's basically what I said, that people have already run your kind of structure motion pipelines on a bunch of data sets. Or you can have synthetic data sets and then there's a bunch of images. So that's it. But I think like the talks before, it's cool to see what you can do. So yeah, I mean, the obvious thing you can do is you can take two images, one here, for example, and one up there, and then you could get a point map of the entire scene. Okay, so now this is also a quiz here. If I have an image from here, I have an image from up there, I have the point map from both of these images in the reference frame of the first image. Can I compute the relative pose between these two images? So, for example, so I have this image up here, I have this image here, and I just have the point maps, right? But I know they're both aligned in this reference frame of the first one. What do you think? Yes or no? Or why? Any ideas? So I have point maps from this image, from this image. I know those are from that image. I know these are from this image, but both are in this reference frame. So they're kind of they talk about the same 3D points. You can do some PNP, some type of solver, so you can do something you have learned in this course. But I'm not so great at these things. But you can do some kind of basically the inverse of triangulation or something like that, and get back to the. So you do get relative poses from this. So you could get. So you can see the cameras here, and you can see the point maps. So it look pretty cool. So just from two images, just 1 second or something, a forward pass, and you'll have a pretty cool representation. Something that they highlight as well is can do no overlap, where images are basically it's impossible to do with your technique. Like if you try to compute SIFT here and do the matching, it'd be pretty bad. So this you can do, so it kind of can learn from the data to infer 3D point maps. So like how should they basically look? And I mean, I think Frederick told me that this might have been made a mistake in their sampling scheme for sampling pairs, that somewhere the non-overlapping pairs in the training data were just by mistake. But it turns out it's pretty cool that you can actually try. The network works even on non-overlapping pairs, so it doesn't need real matches. Well, I recorded a short video when I used one of these like pairwise networks. You can like get these scene reconstructions with the cameras. That's basically what I wanted to show you. But these you could, of course, get from in your assignments. You've also seen these in Python notebooks, widgets, but they look a little bit cooler here. They also get more dense representation from just two images. So in your pipeline, you would need a bunch of images to get these kind of dense point clouds, I would say. That's least. So this one thing. So I'll check, but the last most important follow-up on this work is VGGT, which is very popular, and it extends this work by going to more than image pairs, so going to full image sequences. So now someone in the audience before asked about how long are these sequences usually. So we worked on image pairs, right? This duster acts on image pairs, similar to your pipeline. Then you could chain these together and do some global adjustment and get a nice scene reconstruction. So for example, in this Rome scene, there's perhaps like thousands of images. VGGT, this network, is trained on up to 24 images simultaneously. But then they show that it can, like as I said, also transformer kind of works on sets, so it kind of can extend. You can work on the sets can be as large as you want, and it can still compute this attention mechanism. So you could do VGT for hundreds of images at the same time if you have a GPU VRAM for it. So that's so you could do arbitrarily long sequences. They train on 24 length. Well, we're back at our old friend here with some tokenization and deep learning stuff. But I won't do too much of the details here. But it's kind of similar, exactly the same thing we did it last time. You can downsample the image, going from a higher degree representation with RGB to a lower, coarser representation, but that also contains more semantic information in the tokens. Then you do that for all of the images, and number of images could be 24 in this case. Then you compute attention between all of the different tokens in all of the different images. So this becomes quite long context length. So when you chat with ChatGPT, I suppose the old version of ChatGPT used to only have 1024 tokens that were just their VRAM or something exploded after that, so they didn't want you to. They limited it after that. And here, I suppose, if you have 200 per image and you have 200 images, it's still not so much, right? So it's like, but it's going on the degree of where your token. So it grows squared, right, with the sequence length. So Uh, but yeah, around maybe 10,000 or 20,000 tokens is reasonable to think here that they use. Um, yeah, so they compute attention in the frames and then they compute attention between all of the frames and then you output a bunch of stuff. So here the quiz might fall also flat here, but they compute a bunch of stuff basically. So they compute, have a camera head, so they get out relative poses. So basically, they predict some rotation matrix and translation vector that is in relation to the first image. So similar to DUSt3R, that it has a reference frame. Like that this is the canonical identity rotation, and then everyone else has to pay attention to that one and say what angle they are to them. But then they also do depths, monocular or kind of depths, and depths are basically just 3D point mass, but in the local reference frame of your image, or something akin to that. Then they also produce 3D point maps in the first image, and then they also produce tracks, which are basically matching pairs, matching points that are seen in all of the different images. Well, I already told you before, so I won't ask you, but it's definitely over constrained or like kind of over whatever. Like there's too many things they're predicting here in terms of what they need to do, but they say this is beneficial. But even for the duster, you could just predict the points and then you can solve for the pose and things like that. But yeah, you definitely don't need all of these quantities like depths, points, and cameras. Like some of these are can be solved from the others using what you have learned in this course. Uh, well, yes. So that is it. And VGGT, one of the main things that they also do is that they go from using data that comes from like the RoMa thing, where there's no ground truth really. The ground truth is pseudo ground truth because it comes from a pipeline like what you have done. Whereas VGGT use a real ground truth in the sense that they use synthetic data. And synthetic is, in this case, not so. I mean, LLM people talk about synthetic a lot, but here it's like basically if you play GTA 5, it looks pretty realistic, but it's not the reality. So this is synthetic data, and you compute poses in this game engine and things like that, which are very accurate, and you have great point maps, everything. So this is one way you can do it, and you can imagine a bunch of other ways to get synthetic data from rendering engines. But they use mainly this because then they get very high quality point maps and things like that. So, and then they can also train on real world data and get some generalization. And then here they also say training 2 to 24 frames. They randomly sample between those. So that's what we talked about before. And then you can do inference on how many frames you like, basically, if you have. And also one thing to note, I suppose, is that just for getting a sense of how grand these things are. So this one was trained on 64. I mean 64 A100s, but they were the big version of those ones for over a week. So this is I mean this costs over 1 million crowns definitely in training costs if you would to rent these from AWS. So this is depends on how you see it, but at least for hacking at home, it's a very large investment. And what you can get is these kind of things. But now you can use it very cheaply, right? So I guess that's the point. But so here they do 32 views of some pyramids, and then I mean you get quite dense point maps, and then the color comes not from their predictions, but from the images you kind of project the image or colors onto the point map. So don't be fooled that the network knows all of these things, but it's you can get all these things from it. So here they have 64 views, just takes 1 second, which yeah, as you will see from the project, is shorter than what it would take for traditional structural motion pipeline to get this. Here they even do 128 views. I mean, yeah, but I don't know, this one looks a little strange, but you do it inside some type of, I don't know, religious building or something, and then you get yeah, you can get the full kind of point map from that one. So, yeah, these are some of the examples. Um, Depth anything is newer. I mean, these are basic, as you can see from Duster, they do the kind of same thing. It's like there is one recipe to do it. You use transformers, you tokenize your images, you do some attention between frames in different types of ways, and then you compute point maps plus other things, and you do some parameterization of your output map, and you can think about that very deeply, but they all kind of do the same thing. So there's a bunch of these papers and a bunch of hype around these. So it's quite an interesting, yeah, you can do some, these you can do some SLAM, like simultaneous localization and mapping things like robotic people love, and you can do all these kind of tracking and things. But basically, they have not done. I mean, they do almost the same thing as VGT. Sorry, I guess I don't have a slide on that, but yeah, they just do some other things on the ray maps, how they do that, but basically the same thing in the end, just not computing as many. They do as many images as VGGT, as I just showed you, but they don't predict all of these quantities. They just predict ray maps, which we haven't gone into so much in this course, so we don't need to do that. Then there's some other works that this map anything where you can, if you know the calibration of your camera, for example, that might be of interest. So if you have your iPhone, you can look. It has like it's already calibrated, so you could potentially input this into your reconstruction pipeline, and this is something you could do in this work. So you could condition on, if I know the depth of one of these images, I can input that and stuff like that. But in the end, it does the same thing. It uses some transformer to learn from a bunch of data. Well, this is, I mean, the gist of it. I mean, I'm a PhD student, supervised by Frederick, and so are the two prior speakers. Yeah, we do actually, yeah. I mean, I think one of the things I wanted to also highlight is with the knowledge of this course, you can do some quite, I mean, combined with a deep machine learning course, you do have quite advanced knowledge, I would say, of modern computer vision, especially for 3D stuff. So, yeah, so we do some research on that. I mean, some of the things we have done, I mean, it's definitely mostly these things are actually been run by Linköping for the most part, but we have been part of it. But for example, you could match images that are super hard to match. Like imagine you have like if you look here down, yeah, I guess in the here down in the left corner, you have like a Ukrainian like some governmental building from one direction, and then you have a Ukrainian governmental from the exact opposite direction, and then you want to find matches from this huge, super large wide baseline. And it's like in the night, and maybe here it's in the winter. Like, you know, it could be different seasons and everything. People kind of moved, you know, some construction kind of been done in between, and you want to find matches. And if you use SIFT, you'll run into problems here. So in some of these works, you can show like how you can learn very robust matchers from neural networks. But yeah, I mean, that's the gist of it. And please do ask any questions if you have any. So, and we'll end a little bit early for this session. So yeah, feel free to leave when you want to, but yeah, do ask questions. And we have lab sessions after this now. So yeah, any questions from the audience?